Hello students. I had intended to just produce 4 videos related to free fall. One explaining some things about free fall in general, and then 3 sample problems. But then I found this interesting problem that I thought might be a good idea to share with you. I wanted specifically for you to see that it's an acceleration of 9.81 meters per second squared when something is in free fall on Earth. And in this problem, the object that is falling, a feather, is falling on the moon, and so we will have a different acceleration. Now, you are not expected to memorize the acceleration caused by gravity on the moon, but you are expected to know the acceleration caused by gravity on the Earth. So if the problem is not taking place on the Earth, they have to tell you that. And if the problem has a different value for the acceleration caused by gravity because you're not on Earth, then they need to tell you that number. So in this problem, it says a feather is dropped on the moon from a height of 1.4 meters. The acceleration of gravity on the moon is 1.67 meters per second squared. Determine the time for the feather to fall to the surface of the moon. So this is the second type. We've already gone through that. You know how far it falls. You're trying to figure out how long it takes. So this is very similar to the problem that we did earlier with the penny being dropped from the sky deck of a skyscraper. When we read through the problem, we see pieces of information, 1.4 meters, that's equal to the displacement of the feather. It's a positive displacement. We must be taking the positive direction as the downward direction. The object is going to speed up as it falls down, but since it's not on Earth, it's not going to speed up with an acceleration of 9.81 meters per second squared. They're giving us a different value for the moon, where because of the moon's smaller mass, it has a smaller gravitational pull, and therefore objects don't speed up as quickly when they fall. The A value then will be 1.67 meters per second squared. It says the feather is dropped, and the implication there is that the initial velocity is equal to 0. That's true regardless of whether you're on the moon or on the Earth. Okay, so we have the displacement, delta x, the initial velocity, and a, and it asks us to determine the time. So we're looking for a value of t. And as in the second sample problem that I did earlier, we will find the appropriate equation, which I think is going to turn out to be that one. All right, so check off the pieces of information we know. That is sometimes helpful in identifying the equation. If you know right away what equation you want to use, then you can jump right to that one and get to the math. But if you don't recognize right away which equation you're supposed to use, then this is a helpful method for trying to figure out the correct equation. So we know delta x and vi and a, so we put a little check mark by all of those things, delta x, vi, 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 delta x, a, vi, delta x. I notice there's an a missing from my equation over here. We know that value of a. All right, so it's not possible to use the first equation, not possible to use the second or third equations. We don't have enough information to solve using those equations. We have enough information to use the fourth equation, but that would get us to the final velocity, how fast the object is moving when it hits the surface of the moon. But that's not what they're asking us to find. And so the last equation, as we predicted, will be the best one because we have delta x and vi and a, and we're looking for t. And that equation has those 4 variables in it. There's always well, almost always, more than one way to solve the problem. So if I did use the fourth equation to get VF, then I could take that VF value and use it in the third equation to solve for T. So I could do this as a two-step problem where the first step would be to use this equation to find VF, and the second step would be to use that new VF value in the third equation to get T. But there's no real reason to do the problem in two steps if you can just do it in one step. So we're going to go ahead and use the last equation. Delta x equals VI times T plus 1/2 AT squared. And if you have a VI value of 0, it doesn't matter what T is, because anything times 0 is 0. And so that part of the equation is going to drop out as we continue with our math. 1/2. Remember, this is happening on the moon, so our acceleration is not 9.81. It's 1.67 meters per second squared, and T squared. All right, so delta x equals 0 plus 1/2 1.67 meters per second squared times T squared. So I'm going to simplify one more time by saying 0 plus this term is just equal to that term, and I'm also going to multiply 1/2 by 1.67. And that's equal to 0.835. So 0.835 meters per second squared times time squared. Oh, I forgot to put in my distance. I should have done that way back here, right? 1.40 meters. 1.40 meters. 1.40 meters. Oops. Okay. So now I'm going to divide both sides of the equation by 0.835 meters per second squared, and that will give me the value of T squared. 1.40 meters divided by 0.835 meters per second squared. So the meters will be canceling out, and we'll have 1 over second squared. So 1.4 divided by 0.835 is equal to 1.68 seconds squared. Now that's equal to the time squared, which is not what we're looking for. We're looking for the time. So I need to take the square root of both sides. The square root of time squared is time. The square root of 1.68 is equal to 1.29. The square root of second squared is seconds. So it takes 1.29 seconds for an object to fall, 1.4 meters when it's on the moon.